Yeah, good afternoon. Today I'm going to discuss the addressing modes of 8085 and also the instruction set of 8085 also. So now to start with the addressing modes of 8085, to perform the 8085, any operation we have to
press.
So addressing modes of 8085, to perform any operation, we have to give the corresponding instructions to the microprocessor. In each instruction, programmer has to specify three things. Operation to be performed, address of source of data, address of destination of result. Now, the addressing modes methods by which the address of source of data or address of destination of result is given in the instruction is called addressing modes. The term addressing modes refers to the way in which the operand of the instruction is specified. Basically, the total instruction set is around 106 or so. So, though all those instructions are divided into 5 different addressing modes, so any instruction comes under any one of these addressing modes. The first one, which the addressing mode is the direct addressing mode, and with example we'll discuss in detail. And register addressing mode, register indirect addressing mode, immediate addressing mode, and implicit addressing mode. These are the 5 addressing modes of 8085, which are very important. Now coming to the first one, direct addressing mode. In this mode, the address of the operand is given in the instruction itself. For example, the LDA is an instruction followed by a 16-bit address. Load the contents of memory location 2500 in accumulator. It means whatever the contents of 2500, the data which is there in the memory location, that is to be kept in the accumulator. That is the meaning of that. So directly by addressing the memory to transfer the data into the accumulator. So that comes under the direct addressing mode. LDA is the operation. 2500H is the address of the source, and accumulator is the destination. So whatever is the data available in 2500 address, that will be transferred to the accumulator. This is the addressing modes, direct addressing mode. Next is the register addressing mode. This register addressing mode is example is move A comma B, means the contents of B will be transferred to the accumulator. So move the contents of the register B to the accumulator. So this is this type of instruction. There are so many instructions transferring from one register to other register, which comes under register addressing mode. So in this mode, the operand is in general purpose register. Move is the operation, B is the source data, A is destination. Means whatever is the contents, that will be copied into the A register also. So that is the about the register addressing mode. Next is register indirect addressing mode. In this, the mode, the address of the operand is specified by a register pair. So there is some memory, some data in the memory, that contents will be transferred to the accumulator. Basically, the M has to be defined before this instruction, like LXIH, the corresponding address that particular memory address refers to the memory. So whatever is the data available in that particular address, that will be transferred to the accumulator. Then we call MOV A comma M. So M is the memory location specified by the HL register pair, and A is the destination. So this type of instructions like indirect addressing mode is the example for that. Then immediate addressing mode, whatever the MBIA, 05, this type of instructions, the contents, whatever is from the keyboard, we send data from 05 or whatever is the data that will be shifted to, that will be transferred to the accumulator or B register or any B general registers. That type of instruction comes under immediate addressing mode. In this mode, the operand is specified within the instruction itself. So MBI is the operation, 05 is the immediate data, and A is the destination. So immediately the data will be transferred to the accumulator from the keyboard itself. Then this type of instructions are the immediate addressing mode. Then is the implicit addressing mode. This implicit addressing mode, if address of the source of the data as well as the address of destination of result is fixed, then there is no need to give any operand along with the instruction. So the CMI is the operation and A is the source. So the complementary contents of the accumulator, A is the source and A is the destination. So complementing the component, the data, whatever is there in the accumulator, that will be complemented. So that is the implicit addressing. These are the 5 different addressing modes that will be important. Once again, I repeat the addressing modes: direct addressing mode, register addressing mode, register indirect addressing mode, immediate addressing mode, implicit addressing mode. These are the various addressing modes. Then, coming to the type of instruction set, there are 5 different types of instructions. The total instructions are divided into 5. So these are, some of them are data transfer instructions, some of them are arithmetic instructions, some are branch instructions, some are logical instructions and control instructions. So this data transfer instruction from one register to other register, one and direct addressing and indirect, all those are comes under the different addressing modes. And the data transfer instruction in detail we will discuss. First of all, the data transfer instructions. The move MOV RD, RS, which is MOV. Example is destination register and source register. So from C to B, see whatever is the RS, that register, that contents will be shifted to the RD destination register and the content will be moved. This instruction copies the contents of the source register into the destination register. The contents of the source register are not altered if one of the operand is a memory location. Its location is specified by the contents of the HL registers. So move V, C. So then the immediate addressing move instruction MVI RD, data, whatever is the data that will be transferred to the register, destination register. The 8-bit data is stored in the destination register or memory. If the operand is memory location, its location is specified by the contents of the HL registers. So this is how the data will be transferred from data to the destination register, or data to be stored in the memory also. Before the instruction MVI M comma data, we have to initialize the memory location, then only the M will be defined and the data will be transferred to the M. So we can store some data in the memory also. Then the load accumulator instruction LDA, it means load accumulator, the contents of the memory location specified by a 16-bit address in the operand are copied to the accumulator. So the contents of the source are not altered. So whatever is the contents of the memory location specified by 16-bit address. For example, LDA 2034. So what is the address, whatever is the data in the 2034 address location, that data will be transferred to the accumulator and that completes the instruction. So that moving from the specified address location to the accumulator, this type of instruction also comes under this data transfer. Then LDAX register pair. So there are three register pairs are available with F085. One is BC as BC one pair, DE another pair, and HL. There are the three pairs are available. So in this, whatever we store the data in the BC pair or DE pair or HL pair, that will be taken as the address of the memory location, and the corresponding data will be stored in the accumulator. So this type of indirect addressing also can be converted from the memory location data into the accumulator. So the LDAX-B, LDAX-D, LDAX-H are the three instructions. So in these three instructions, the BC pair or DE pair or HL pair, whatever is the address specified, that will be the data specified as taken as address, and in that address, in the memory location, whatever is the data available in that particular memory address, that will be transferred to the accumulator. That is the importance of this particular instruction. Then LXI-H or register pair, LXI-B, LXI-D, or LXI-H. These are the three instructions possible. So this instruction, either any of the pairs, we can store with 16-bit data. So LXI-B with 2034 data. So B will be stored with 20 and C will be stored with 34. So like that, we can store at a time the 16-bit data into any one of the BC pair or DE pair or HL pair. So this is register pair. This also comes under immediate addressing. Then load H and L registers direct. So the instructions copies the contents of the memory location pointed out by the 16-bit address into L and copies the contents of the next memory location into H register. The contents of the source memory location are not altered. So these data load H and L register direct, copies the contents of the memory location pointed out by 6-bit address into the L and copies the HL, whatever is the 8-bit, 16-bit contents will be stored in the memory locations. Then STA, store the accumulator content direct. So whatever is the accumulator content specified by STA 16-bit address, specified by a 16-bit address, that is 2050. So STA 2050, whatever is the, after any operation, any addition or subtraction or any operation, if the contents are there in the accumulator, that will be stored in the specified memory location specified by the STA 2050. So in 2050, the contents of accumulator will be stored. Then opposite to this STAX RP, register pair, either stacks B, STX D, STX H. These are the three possible instructions we can write. See, whatever we specify the register pair, whatever is the content in the HL pair or DE pair or BC pair, in that particular address, the contents accumulators will be stored in that particular address location. The accumulator contents are stored in the address specified by STAX. So the contents of the accumulator are stored in that particular register memory location. So contents of the accumulator are copied into the memory location specified by the contents of the operand or register pair. The contents of the accumulator are not altered. Then store H and L registers direct. The contents of the register L are stored into the memory location specified by the 60-bit address in the operand, and the contents of H register stored in the next memory location by incrementing the operand. The contents of the registers H and HL are not altered. This is a 3-byte instruction. The second byte is specified by the low order address, and the third byte specifies the higher order address. So HLD, SHLD. So this H and L contents will be stored in the memory location. Next, exchange H and L with the DE. So the contents of HL or exchanged data will be, whatever is the data in H will be transferred to D, and whatever is L will be shifted to E, and vice versa. That is, D contents are moved to H and E contents will be L. So the contents of register H are exchanged with the contents of the D, and the contents of the L are exchanged with the contents of the E. So this is a exchange instruction. Then copy H and L registers to the stack pointer. So the stack pointer instruction loads the contents of the H and L registers into the stack pointer register. The contents of the H register provide the high order address, and the contents of the H register provide the higher order address, and the contents of the L register provides the lower order address. The contents of the H and L registers are not altered. So this is about HPLL instruction, not followed by any data or anything. Then exchange HL with the top of the stack, exchange TL. The contents of the L register are exchanged with the stack location pointed out by the contents of the stack pointer register. The contents of the H register are exchanged with the next stack location. However, the contents of the stack pointer register are not altered. Then this is all for the push register pair into the stack. So the stack is whenever we write a subroutine program, so we store this information with the contents of the main program into stack area, which we, by writing the push instructions, so all the data will be stored in the stack. And after entering end of the subroutine program, we will retrieve the data from the memory locations, that is subroutine, and then we will call back that is by pop instruction. We can get the data in the memory, whatever is there in the main memory, main program, that will be again continue the main program, and then it will be done. So the contents of the register pair designated in the operand are copied into the stack in the following sequence. The stack pointer register is decremented, and the contents of the higher order register B, D, H, A are copied into the location. The stack pointer register is decremented again, and the contents of the lower order register are copied to that location. So push B or push A, push C, push E, something like that. Then after completing this instruction, this subroutine, again we have to get back all the data. So that data by pop of the stack register by instruction pop by register pair. So the contents of the memory location pointed out by the stack pointer register are copied to the low order register. So the CEL status of the flags of the operand. The stack pointer is incremented by 1 and the contents of the node location are copied to the higher order B, D, H, and A of the operand. The stack pointer register is again incremented by 1. Then this in and out instructions both are useful when the processor to the IO device. If you send data out or if you want to receive data, you can write these instructions. These two instructions, in and out, are the two instructions useful in transferring or getting the data from the IO device. So out instruction followed by the port address. We have to specify the address of the port that are IO port. So the contents of the accumulator are copied into the IO port specified by the operand. So whatever the contents of the accumulator only we can send out, or we can receive by writing the instruction in from the port 8-bit address. So input data to the accumulator from a port with the 8-bit address. So contents of the input port designated in the operand are read and load into the accumulator. So these are the two instructions which we can store or we can load the IO device, or we can get the data from the IO device. So these are some of the on the instructions. So let us write one program for this move data instruction. So MVI A, 05, then MVI B, 08, then MOV C, A, then MOV D, B, then HLD. So this is the simple instruction. So I'll ask this is the assembly program, then I'll write the assemble. So this is how the program, this is the address, and then this is the mnemonics, and this is the corresponding hex code. 3 is the hex code for move immediate A content 05 into the accumulator. So this is the instruction, this is the data. Similarly, 06 is the instruction to get the data, to load the data. 08 into B register is 06. Then data will be 08. The next instruction is the contents of the accumulator are copied to the C register. Then the other register, contents of B is copied to the B register, then halt the program. Now, if I execute the instruction MVI A05, the accumulator 05 is stored in the accumulator. Then again, next instruction, here itself the program counter also we can show. At the last class, we discussed the importance of this. So C002 is going to be executed. The 00 address the contents of 06. So this is executed now. So 08 is stored in the B register. Then this is going to be executed, move the contents of A to C. So 05 should be connected to this register. So let us see. Yeah. So C is copied the components of A with C. Then next section is going to be executed. Move D comma B. So B registers are copied to D register. So this is the all about and halting the program. Then let us see that the program is switched off, that is halted. So this is how the program is completed. This is the memory location. So in the starting program, C00 is the starting address of this. So the memory is starting for users area. It is C000 to CFFF. And from this is C3E and 05, 06, 08, 04F, 5076. These are the hexadecimal numbers stored in this particular memory location corresponding to this. Each time it gets the data and puts in the processor. So every time the processor sends the address of the uh, location to be retrieved, so get the information from the memory to the memory and to the instructions. So this is the memory. So every time whatever we write the program here, that will be stored in the memory location. And once we execute by instruction, it gets the information from the memory and keeps in the corresponding location. And then it will be executed one by one instruction by one instruction. So this is all the data transfer instructions. Then let us discuss some of the instructions of the arithmetic instructions. The arithmetic instructions are add instructions, adding the contents, add register or memory to the accumulator. So in any of these instructions, accumulator is very important and the contents will be added to the accumulator only. So add B, it means the contents of B will be added to the contents of A. So the section overall you can say add R, the contents of the operand are added to the contents of the accumulator and the result is stored in the accumulator. If the operand is a memory location, its location is specified by the contents of the HL register. Then all flags are modified to reflect the result of the addition. So add M is such an instruction which before the write the add M, so it has to be initialized by writing the let's say H. So that HL pair, whatever is the data in the HL pair, that will be considered as the address of the memory location, and the corresponding data is called M. That is the memory location data. So that data will be stored, will be added to the contents of the accumulator. So this is add M or add any register content. So M to the A contents or R to the A contents. R for any register like A, B, C, D, E, H, L. So all these instructions useful this. Then add register to the accumulator with carry. Whatever is the addition that is going to perform to contents of the accumulator to the register, and the carry also will be added to this. Suppose if it is the contents of B are added to this along with the carry flag. The carry flags are added to the contents of the accumulator and the result is stored in the accumulator. The operand is a memory location. Its location is specified by the contents of the HL registers. So all flags are modified to reflect the result of the addition. So in this similar instruction like add or, but the contents of the carry flag also will be added to this particular data. Then coming to the add immediate to the accumulator. So any 8-bit data from the keyboard to the accumulator will be added directly, which is similar to the add B only, but the 8-bit data is added to the accumulator content directly. So let us see one example for this. So move immediately, then I will say here add B. So here both the contents are added to the register. So then I will store this C050 address location, and then I'll say hard. So let us assemble this program, and this let us discuss again in detail. So move A, comma 05. So 5 will be stored in the accumulator, and then 08 is stored in the B register. Then B contents are added to the accumulator, and accumulator contents are stored in the C050 address location, and then finally the program will be stopped. So let us uh, execute this. The first section, after executing, the accumulator is stored with 05. Then B register is stored with 08. Then the 08 is added to the A register, and A contents of this instruction will be 0D because it is a hexadecimal number. The hexadecimal number after 109, it will be 10, and 0A, 0B, 0C, and so on. B, C, D, E, H, D, E, and F, up to F only. So 10 is equal to A, 11 is in decimal, 11 is B, 12 is C, 13 is D, and 14 is E, and 15 is F. So these are the hexadecimal equivalent numbers. So after executing add B, then STA C050, if you execute it, then the location, this location to be loaded with the contents of the that is 0D is stored here. So that is what the program is halted. So this is what the instruction is. Then instead of this section, I will write ADI 08. So I can remove this section. So again, assemble the program. Then this also gives the same result. Let's see this 05, 08, 0D, and directly it is added, and the contents of this is added. So this is how the instructions are. So add immediate is this. Then ACI, add immediate to accumulator with the carry. With carry. So the 8-bit data and the carry flag are added to the contents of the accumulator, and the result is stored in the accumulator. All flags are modified to reflect the result of the addition. So the add immediate law, this Now, let us continue this. This is discussing the arithmetic programs. So, arithmetic instructions in this add with the immediate carry. So, 8-bit data. So, and the carry flag is added to the contents of the accumulator, and the result is stored in the accumulator. All flags are modified to reflect the result of the operation. So, the data, 8-bit data, which is from the keyboard to the accumulator, along with the carry to be added. Then DAD register pair, the 16-bit contents of the specified register pair are added to the contents of the HL register, and the sum is stored in the HL register. The contents of the source register pair are not altered. If the result is larger than 16 bits, the carry flag is set. So other flags will be reset. So they add register pair to add register pair to the HL register. The contents of the two will be added to the HL pair. So stored in the HL register. Then is sub R. Similarly, add B, like add B, we have sub B, sub C, sub D, sub E, all those instructions. The contents of the accumulator are subtracted from the accumulator contents. So the contents are subtracted from the accumulator contents, any register contents. So, and also similar to the sub M. So the memory specific is specified by HL pair. So that is considered from memory to the so subtracted from A minus B, it will be RA minus A, RA minus R. So this is how the contents of the operand are subtracted from the accumulator contents of the accumulator, and the result is stored in the accumulator itself. If operand is a memory location is specified by the contents of the HL register, all flags are modified to reflect the result of the subtraction. Then SBB. So subtract the source and borrow from the accumulator. So SBB are, and if the contents of the operand and the borrow flag are subtracted from the contents of the accumulator, and the result is placed in the accumulator. If the operand is a memory location, its location is specified by the contents of the HL pair. So it will be the borrow and the register pair. All those are subtracted from the contents of the accumulator. So sub R, sub M. So all is SBB. So subtracting the source and borrow from the accumulator. So the source register is any of the registers like B, C, D, E, H, L. So all these are subtracted from the, along with the borrow. So it will be subtracted. Then SUI, subtract immediate from the accumulator. A 8-bit data from the keyboard will be subtracted from the accumulator. Then contents of the accumulators are, the result is stored in the accumulator only. So the flags are modified to reflect the result of the subtraction. So the contents, finally, the result will be available in the accumulator only. Then SBI, subtract immediate from the accumulator with borrow. So a 8-bit data and the borrow, if it is present during that particular time, then all these will be subtracted from the contents of the accumulator, and the result will be stored in the accumulator only. So this is how the SBI 8-bit data works. So next is the increment register or memory by 1. So INR A, INR B, INR C, any contents of the, any register contents can be incremented by 1 using this instruction. INR A, INR B something like so. ANR M is also possible. So it will be incremented 1 only by 1. If it is 65, then it will become 66. That's it. So this is how this. Then instruction INX R. So X R is any register pair, that is HL pair, DE pair, and BC pair. So only one incremented by 1 only by this instruction. INXH means if it is 2500 is the instruction, then after the contents INXH, it will be 2501, it will become. Then DCR. So the contents of the similar to the INR, this is the decrement. So one number will be decremented by 1. Any memory register or any register contents will be decremented by 1. So DCR, DCRM, this is one increment decremented by 1. So if it is 66, then it will become 65. Any contents, any register specified by R, not any register. Then decrement register, this is for pair. DCXB, DCXD, DCXH, these are the possible instructions. So in DCXH, then DCXH, then HL contents will be decremented by 1. Then DAA, decimal adjust accumulator. So I'll stop here this today. So this is a disturbance.